All right, folks, it's time for some really important work. Make sure you've got pen and paper ready to write down some notes. Remember, pause the video as you're going. Give yourself time to write down important things. I'll be checking to make sure that you've got these. I know what we're doing today will seem pretty simple in the end, but it's a big building block for things we're going to use all semester long. So be ready to write, be ready to pause, and let's truck forward. Today what we're going to do is we're going to build on this idea that organic compounds are made of carbons connected to each other, and usually to hydrogen atoms. Once in a while there's a few other things thrown in, but typically carbon and hydrogen make up the bulk of what we're going to work with. When chemists name organic compounds, they follow certain rules. It's a lot easier than trying to name each compound individually. If you've got a set of naming rules, it can apply to millions and millions of compounds without having to memorize them all individually. So, when we're naming organic compounds, the important thing to remember is that the name tells you how many carbons there are that you're talking about in that compound. The name and the number are paired together. If we know the name, we know how many carbons. If we know how many carbons, we can know the name. So let's get rolling. You got to write this down. These 10 prefixes are going to be a building block for our entire semester. Pause long enough to write this. You'll have to memorize it. You'll have to know it. It won't be something you can guess at or pause to look up as we get rolling forward. This is the first important thing to stick in your brain. Each one of these prefixes represents a number of carbons. If you see the prefix meth, it's a one-carbon group. The difference between an amphetamine and a methamphetamine is a one-carbon group. 2 carbons is ethanol, the alcohol that's in wine and beer and things like that, is a 2-carbon alcohol. Propane, as one would use for grilling with their propane accessories, has 3 carbons. Bute, like butane that's in a lighter, has 4 carbons. You get the pattern. Each of the prefixes tells us how many carbons there are present. Pause the video long enough to write this stuff down. You'll need it. So, what do we do with these? That first part of the name, the prefix, will tell us how many carbons we have. In this example, I have 5 carbons bonded singly to each other. It's not the whole picture, but it's the carbons. That's what we care about right now. Because I have 5 carbons, this compound will start with the prefix pent. The second part of the name tells me how the carbons are connected to each other. In that last example, each of our carbons was connected with one bond, a single bond. So the name of that compound is going to end in ane, the suffix ane. That indicates it's part of a group known as an alkane, a family or functional group that all has carbons connected by single bonds. So I've got 5 carbons connected by single bonds. That compound is the basis for pent and ane to be pentane. Pretty simple. Let's try it out. Let's see how you do. Try this one. Look up how many carbons you have and what the prefix that goes with it. Look to see how the carbons are connected and name the compound. Pause till you're ready. Here's an answer. If you wrote propane, you're right. If you didn't write propane, you are wrong. Even if you knew it but didn't write it down, you made a terrible choice. You should write this stuff down. Try this one. 6 carbons connected by single bonds. The prefix for 6 is hex. Single bond connected means they're anes, so hexane should be our main choice. Now, I'm not really telling you the whole picture. That's not really propane. It's not really hexane. I didn't do that because I'm a hateful liar. I wanted us to focus on just the carbons. But remember, our first rule of organic chemistry is that carbons will always have 4 bonds. They always have 4 valence electrons that they're available to bond with. So carbon is going to have 4 bonds. So what about the rest of the space? Hydrogens. Typically, if I've got the room for extra bonds to happen, a hydrogen can tag right on the end of that extra bond. So I've got 5 carbons and enough hydrogens to fill in the empty spaces, so that every carbon has 4 bonds. Now the formatting on this is a little odd. On these hydrogens, each hydrogen is connected to a carbon, but the hydrogens are not connected to each other. So be a little careful with this one. You notice if you follow each carbon, there are 4 lines sticking off of it. Each line represents a pair of electrons that either connects it to another carbon or to a single hydrogen. This is a full view of pentane. So now that you're a professional at this, try to draw butane and octane, each with the right number of carbons, the right type of bonds, and the right number of hydrogens to make sure that every carbon has 4 bonds. Don't just skip this part. Pause it and do it. No, really, pause it and do it. Make sure you can do it. I'm not kidding. I will find you. All right, here's the answer. Butane. But means 4, and the ane means those 4 carbons are single bonded to each other. And then I've got single lines sticking off showing all of the places where hydrogens can bond to the carbon so that we have a full 4 bonds on every single carbon. For octane, wow, that's giant. It's obnoxious, but it has 8 carbons, all single bonded, and enough hydrogens to make sure that every carbon has 4 bonds sticking off of it. Don't get lazy. Take the time to draw the hydrogens. Remember, they have to be capital letters. Look at your drawing. Did you take the time to draw in all the hydrogens? Did you draw them as capital letters? If the answer to those is yes, good. If not, maybe retry it. I will come find you. I'm just kidding. Alkanes, all right, here we go. I probably shouldn't record these late at night, huh? Yeah, we'll talk about it on Monday. Anyway, alkanes always have a ratio of carbons to hydrogens that's pretty predictable because of the number of bonds that carbons can have. The formula looks like this, where N represents the number of carbons. So no matter how many carbons we have, I have twice as many plus 2 hydrogens as I do carbons. So C2H6, in this case, N is 2. If I double it and add 2, I get 6 hydrogens. So a 3-carbon compound that's an alkane, how many hydrogens would it have? Well, I've got my formula, 2N plus 2. N is 3, so that gives me 8 hydrogens. So that means C3H8. It's not too bad. Try this one. Do it. Seriously, pause this, write it down. You've had enough time. Not too bad. Gives us C4H10. The value of this is it lets you check the structure you've drawn. If you know how many carbons you have, you know how many hydrogens you should end up with. And no matter what funky thing you do with the structure, if you've got the right number of carbons and the right number of hydrogens, you've probably put the bonds in the right place. This is especially value in cases like this, where the compound is so big, there's no way you're going to draw it out. No matter how many times I ask you to pause this video and draw that, I know there's no way you're going to draw a C50 string unless you are really, really bored, maybe need a hobby. So how many hydrogens will there be? 2 times 50 plus 2 for 102. And this would be a 50-carbon alkane. Whoa. Really handy when we get to numbers beyond 10. Now, there are names for carbon compounds beyond 10. We're really not going to worry about a lot of them in this class. We'll have things with more than 10 carbons, but not in one little string, and that's really what matters. So octane. Draw a structure for octane. Write its formula. Remember that oct means 8? 2 times 8 plus 2 is 18 hydrogens. C8H18. You can look back at the structure you drew for octane earlier, count the hydrogens, see if you actually have 18 of them. Whoa. Try this out. Propane. Prop is 3 carbons, so C3 is the first part. Ane means that the number of H's are 2 times that, plus 2, for 8. So propane is C3H8. All right. Now, here's where I've got a challenge for you. You can play with those strings of up to 10 carbons all you want, but it gets trickier than that when you start to realize that not all of your carbons have to be in one straight line. So here's your homework assignment. I want you to draw 3 different structures that each have the formula of C7H8. H16.